Today we will talk about radicals, and let us start by having a little mini review as to what the chemical bond represents and what it is. You may recall from general chemistry that when you do combine two elements together, you do form a bond. If the elements are nonmetals, the bond is regarded as being covalent. But the picture is a little bit more intriguing than just saying this is covalent or ionic, because what you can see here in this framework, right? If you combine fluorine with fluorine, you get a bond enthalpy, which is the energy required to break that bond into radicals of 155 kilojoules per mole. And then that kind of increases and it starts decreasing a little bit. But the idea is that if you start mixing atoms of different kinds, so for instance, fluorine with chlorine or chlorine with bromine, etc., ideally, if the story was that you're just sharing electrons and that's the end of the entire premise, then what you would expect is that if you were to have these amounts for the bond enthalpies and you simply add the halves of the corresponding elements. So for instance, let's say you're talking about the fluorine chlorine molecule. If you have 155 and you have 240 and add them together, you would expect that should be the bond enthalpy of the species, right? So in essence, take the average of the bond enthalpies of these values. And the interesting thing, yeah, if you do that, is that, okay, you find out that the values for like fluorine with chlorine should be 197. The values for fluorine with bromine should be 172. Those with fluorine and iodine should be 152. And if you compare them to the actual values, these numbers are substantially smaller. For some of them, they're kind of close, like in the case of chlorine with bromine. But chlorine with iodine, the values are definitely different. So there is a discrepancy. And the fact that when you combine fluorine with the other halogens, you get the biggest discrepancies is all due to the fact that the electronegativities of these elements are different. So in essence, the covalent bond is actually a mixture of sharing the electrons, but also of an attractive interaction between an element that develops a partial negative charge as a result of its greater electronegativity, and the other element that loses, partially an electron and develops a partial positive charge as a result of being less electronegative. So, technically speaking, the covalent bond strength is dictated by both the covalent factor and the ionic factor all in one. And this is a much more complete picture of what the covalent bond actually is. Now, Pauling, the same Pauling that came up with the electronegativities, gave us also a means to kind of quantify this ionic contribution to the covalent bond with the electronegativity values depicted here by the symbol chi. So you have the electronegativity of one element, element E, let's call it, the blue element, and the electronegativity of the element X. If you take the difference of those two electronegativities, that should, in essence, give you that partial positive or partial negative charge that you're developing as a result of pulling the electrons in towards one of the atoms. And the magnitude is the same, but the charge is obviously different, right? So delta minus and delta plus develop on the two different elements, but they are of relatively equal magnitude. So you could, in essence, say, well, if the ionic contribution is simply a constant multiplied by the charge of the positive species times the charge of the negative species, which is in accordance to Coulomb's law of electrostatic attraction or repulsion, depending on which charges you're dealing with, you can simply plug in the difference of the electronegativities for your delta plus or delta minus, and in essence, you end up obtaining this square term of the difference in electronegativities. Now, the value that I'm depicting right here, 96.5, it's a little bit of an extrapolation based on experimental data that I don't necessarily want to get into right now. And in fact, we're not really going to be using this equation to do calculations. But the point is that the change in electronegativity does contribute a positive amount to the enthalpy of the covalent bond. And when you have highly electronegative elements, combined with lesser electronegative elements or elements that have low electronegativity, you do develop um, bigger delta pluses and delta minuses, which allows you to ultimately keep this bond tighter together, and it makes it a little bit harder to break. Therefore, the bond enthalpies do increase. All right, so that's kind of the big idea. That electronegativity is really gonna, make a play a role in making the bond stronger, but it's also gonna allow us to explain why it is that in certain molecules the bond enthalpy is gonna be lower than in other ones. And we'll have to, as you'll see in a little while, we're gonna have to implement the ideas of the Vesper shape of the molecules, the hybridization of the carbons. We might even need to invoke some homolumo interactions with the frontier orbitals. So this should be a good overview of how a chemist really looks at molecules. We really think of the molecule as the main actor in the movie, right? That's the lead actor, and the calculations, which we're going to do, some calculations towards the end of the lecture, are there to corroborate what we're seeing in terms of what we know about the molecule. But it's really all about the molecule. Like, what is the molecule doing? How does the molecule look like? And so that's going to be the main premise for the next video, where we'll talk about what happens about um, you know those particular bond enthalpies of dissociation for each one of these type of bonds. We're going to talk about homonuclear diatomic molecules, where we're breaking the bond between the two elements of the same kind. We're going to talk about potential binary acids, or molecules that contain a hydrogen bond to some other element. We're going to talk about methyl uh, bonds, or carbon bonds to some other elements. And we're going to, at that point, move on to talking about different kinds of carbons, like there's some classifications that I'll introduce in the next video. So without further ado, let's stop right here, and I'll see you on the next video.